So today I'm going to talk about Mantis, automatic performance prediction for smartphone applications. I'm Kwon from Microsoft. This is joint work with students, faculties, and researchers from Seoul National University, UT Austin, Intel, and Georgia Tech. So we use third-party mobile apps every day. Predicting the performance of these programs has many applications. We can notify accurate estimated completion time to users, or schedule and manage resources better with prediction, and make a better decision on computation offloading, to name a few. So in this work, we look at a performance prediction problem. Let me define it precisely. The problem we are looking at is to predict the execution time of a program on a given input before actually running the program. That's the problem we are looking at. Throughout the talk, when I say performance, I mean execution time. There are many techniques proposed for predicting program performance. We can classify them into two kinds, differentiated by features chosen to model program's performance. The first approach, features are automatically extracted for domain-specific programs. Examples are operation counts in database queries and network packet header values in network trace analysis. The second approach, it applies to general-purpose programs, but users need to manually specify what features to use. For example, users manually write code to generate features. For the performance predictor design space, we can consider four dimensions: applicability, automation, accuracy, and the efficiency. Here, efficiency is about how quickly we can predict. As we discussed already, applicability is about general purpose versus domain-specific, and automation is about automated versus manual. Approach 1 is not generally applicable, but automated. Techniques in this group have varying accuracy and efficiency. Approach 2 is generally applicable, but manual. Again, techniques in this group have varying accuracy and efficiency. With our system Mantis, we achieve all the four properties. Mantis is general purpose, fully automated, highly accurate, and efficient. In this talk, I'm going to tell you how we built such a system. For the rest of the talk, I would like to first give you a high-level picture of our system. Then I'll present the components of the system, visual instrumentation, profiling, prediction modeling, and predictor code generation. Finally, I will present how accurate and efficient Mantis predictors are with multiple mobile apps running on a smartphone platform. So what is our key insight? One insight that makes Mantis fly. What we observed is that program execution runs often contain features that are correlated with performance. And also those features are computable automatically and efficiently. In Mantis, we take a new white box approach to automatically generate program performance predictors. Let me give you intuition with a few examples. Here we have a for loop that executes heavy computation n times. The value of n is potentially correlated with execution time. This variable value can be a feature. It is automatically computable from program execution. Let's look at a slightly different example. In this for loop, the heavy computation is executed when the branch condition is true. The count that evaluates how many times the branch condition is true is likely to be correlated with execution time. Again, this count is automatically computable. But how about the cost of computing that count? We want to predict execution time quickly before actually running the program. If a prediction takes time to run the entire program, it's not useful. No problem. If we can get rid of heavy computation in computing the branch count, we can compute the count cheaply. So the feature value can be cheaply computable. So to summarize, we extract from execution runs features that model performance accurately. And the features can be automatically and cheaply computable. To implement this idea, we need to address a few challenges. First, what are good program features for performance prediction? Second, how do we model performance with relevant features? Third, how do we compute features cheaply? Fourth, how do we automatically generate predictor code without involving human? So Mantis addresses the challenges by combining techniques from program analysis and machine learning. Mantis consists of an offline component that creates predictors and an online component that uses the predictors for predicting execution time. The offline stage has 4 modules: a feature instrumenter, a profiler, a performance model generator, and the predictor code generator. First, the feature instrumenter takes the program and feature schemes as input and generates an instrumented program. Next, the profiler takes the instrumented program and a set of inputs. It runs the instrumented program on each input and produces feature values and programs execution time. The model generator performs sparse linear regression on the set of feature values and execution time. It produces a function that approximates the program's execution time using a subset of features. As a final step, the predictor code generator produces a code snippet from the instrumented program to efficiently compute the function using program slicing. If the predictor running time is below the threshold TH, say 2% of the original program execution time, Mantis outputs the predictor code. If not, it notifies the model generator features that are expensive to compute. The model generator reruns, excluding those features. So let's look at the details of the modules one by one. First, feature instrumentation. Currently, Mantis uses 4 feature schemes: branch counts, loop counts, method call counts, and variable values. Branch counts are useful since execution time changes depending on control flow. Here, the original code does lightweight computation or heavyweight computation depending on flag. In the instrumented code, for each conditional occurring in the program, we add 2 counters, one counting the true branch and the other counting the first branch. Loop counts. Here we have the original code that reads lines and performs search for each line. For each loop occurring in the program, we add a feature counting the number of times the loop is executed. Method call counts. Here the original code is a function called process. In the instrumented code, we add to the method body a feature counting how many times this function is called. Straightforward. Finally, variable values. For each variable of primitive type, we track the sum of all values returned to the variable and the count of writes to compute the average. So if a variable is set once, say for configuration, the sum returns the exact value written. So we instrument variable values for a few reasons. The variable values capture input parameters and configurations. These values tend to affect program execution by changing control flow. Second, since we cannot instrument all functions, the values of parameters to such functions may be correlated with their execution time contribution. These types of variable values enables us to perform black box prediction for the functions of a program's execution we cannot analyze directly. Third, variable value features may be equivalent to other types of features, but they are much cheaper to compute. Second, the profiling stage. This stage runs the instrumented program with input data. This stage is straightforward. Third, the model generation stage. For performance modeling, we expect a small set of features to explain performance among lots of features. So we use our sparse regression method called SPOR-FOBA. We show that this algorithm performs better than prior sparse regression methods such as lasso and FOBA. So what is our trick? SPOR-FOBA works in 2 main steps. We first prune features by FOBA, sparse linear regression, to filter out unimportant features. FOBA minimizes residual sum of squares with model regularization parameter. So this model regularization parameter penalizes complex models, and we end up with simple models. Then our trick is we perform degree-deep polynomial expansion of selected features to generate terms for the next regression. So for example, here we have selected features, x1 and x2. If we set degree d to 2, we expand 1 plus x2 powered by 2. And this gives us basis functions 1, x1, x2, x1 square, x2 square, x1 times x2. So the next regression function becomes the y hat in the slide. This board part captures interactions among features, as well as nonlinear effects of features. As a final step, we run FOBA to choose the linear function of the terms that meets our convergence criteria. The final stage is the predictor code generation part. We use static program slicing to automatically generate predictor code that executes efficiently. Slicing also enables us to use features that occur late in the execution of the original program. So what is a slice? It's a subprogram of the given program that yields the same value of variable v at program point p. So we want the smallest subprogram that meets the slicing criterion, variable v and program point p, with static program slicing. Let's look at an example. Here we have a program that prints x at the end. Depending on branch conditions b1 and b2, different statements in the middle are executed. After that, x is set to 40, and print x will display 40. If we look at a subprogram that yields the same value x at the exit point, we can slice away the middle and create a slice that does the same. So the slice can be quickly computed. Let's look at the example we saw in the beginning of the talk again. Here, the program opens an input text file, reads each line in the file, and performs an expensive computation on it. Assuming the number of lines in the file is strongly correlated with execution time, the only highly predictable feature here is the Mantis loop count. Naively computing this will take time to execute the entire program. Slicing this program for the feature Mantis loop count and exit point can create a slice that excludes the process core. In this case, the feature is fundamentally cheap to evaluate, but slicing is required to do so. Computing a slice involves computing data and control dependencies for the slicing criterion, and excluding parts of the program that is neither data nor control dependent for the criterion. So why is slicing hard? There are multiple challenges: procedures, heap aliasing, and concurrency. For inter-procedural analysis, we want to propagate dependencies across only realizable procedure path. With aliasing, we need to figure out that references are pointing to the same memory location. So aliasing can cause false dependencies. With concurrency, multi-threaded programs can have inter-threaded data dependencies. All these issues can cause false dependencies. In addressing these challenges, we aim at reducing false dependencies to obtain more precise slices while meeting the scalability requirement. So exact static slicing for language like Java is undesirable. So an inexact solution is inevitable. So we try to find a balance between completeness, soundness, and scalability. In addition, we have to create slices that are executable. Past work on slicing is usually for understanding and debugging programs. Those slices are not executable. But for our cases, the Mantis slice should be executed to predict execution time. We implemented the slicing algorithm by putting together the solutions that address the challenges. There are a lot of details to make this work. At a high level, we have 5 steps. For intra-procedure, we construct program dependency graphs that track data and control dependencies between statements inside each procedure. For inter-procedure, we construct a system dependency graph by stitching together all these PDGs. For context sensitivity, we augment the system dependency graph with summary edges that gives a function core context. Then we run the two-path algorithm on the augmented SDG to create a slice. The basic slicing algorithm is run on intermediate code for easier analysis. Finally, we change the intermediate code to final code. In the paper, we describe the slicing algorithm in detail. There are a lot of details. Due to time constraints, I'm not going to explain each step here. Please look at the paper for details. So that was the description of Mantis. Next, I'll describe the implementation of Mantis and its evaluation. We built Mantis to work with Android applications. in Android, you write a program in Java with Android SDK. And that's compiled into Java bytecode, then it's compiled down to Android Dalvik bytecode. We built our offline component in this environment. Feature instrumenter, profiler, and model generator are built using Java bytecode rewriting tool, scripts, and Octave respectively. The slicing part is built on J-code that uses data log to generate quad format slices. We convert them to Java bytecode slices through Jasmine. Lastly, Java bytecode is converted into Android Dalvik bytecode. We evaluate Mantis in terms of prediction accuracy and predictor execution time. We measure prediction accuracy by computing prediction error. It's the mean of the absolute value of the difference between actual and predicted execution time divided by actual time. Prediction time is computed by the mean of predictor running time divided by actual original program running time. So for prediction accuracy, we show the benefit of nonlinear terms in the performance model and the benefit of slicing. For predictor execution time, we show the benefit of slicing. That is how quickly prediction can be done with slicing. We also show prediction on different smartphone hardware platforms and prediction under background load. Finally, we report Mantis offline component processing time in the work. Due to time, I'll present experiment results showing the accuracy and efficiency of Mantis and the benefits of slicing. For the other results, please look at the paper. To evaluate Mantis, we chose 6 mobile applications. Encryptor basically does encryption on data, path routing that finds a path on the map, spam filter, chess engine, ringtone maker that generates a ringtone from a WAV file, and face detection. The default smartphone we use for experiments is Galaxy Nexus running Android 4.1.2. For each application, we use 1,000 randomly generated inputs that give 95 to 100% basic block coverage of the application. We use 100 inputs for training and set the predictor execution time threshold of Mantis to 5%. First, prediction error and prediction time. Mantis achieves 2.2 to 11.9% error by executing predictor cost at most 1.3% of original application execution time. So prediction time is low. Without chess engine, we have 5% or better prediction error. So Mantis is overall accurate and efficient. Then why does chess engine has higher prediction error? Chess engine's execution time is related to the number of leaf nodes in the game tree. This feature can only be obtained late in the application execution. And there, we cannot find any chip slice with our current system that can compute the feature. So instead, Mantis uses an alternative feature, the number of nodes in the second level of the game tree, that meets the predictor execution time threshold. Now here's the number of detected features and the number of chosen features. As you can see, Mantis selects a few features out of many that captures the estimation power of program execution time. For example, face detection has 107 features, but Mantis chooses 2 features for modeling. So Mantis generates compact models. Next, to show the benefits of slicing, we compared Mantis with the following 2 baselines that use the same machine learning model without slicing. So first, partial execution runs the instrumented program only until we obtain the chosen feature values. This shows the improvement of prediction time thanks to slicing. Second, bounded execution runs the instrumented program for amount of time the Mantis predictor runs. This shows the improvement of prediction accuracy because of slicing. First, Mantis and partial execution. As you can see, for the first 4 applications, Mantis significantly improves prediction time. So for example, for encryptor, partial execution time takes the original program execution time. But Mantis predictor runs for 0.2% of the original program execution time thanks to slicing. Next, Mantis and bounded execution. Again, for the first 4 applications, Mantis improves prediction errors significantly. For example, for path routing, Mantis reduces prediction error from 64% to 4.2%. There's much work on predicting system behavior. There's research on modeling performance or resource consumption in databases, cluster computing, networking, program optimization, and so on. Also, non-trivial features are used for modeling program complexity, hardware simulation specificity, cooperative bug finding. There's also much work on worst-case behavior prediction in embedded real-time systems. In contrast to prior work, Mantis automatically generates accurate and efficient performance predictor code for general-purpose programs. To wrap up, in this talk, I presented Mantis, a framework that automatically generates accurate and efficient program performance predictors. Mantis extracts information from program executions. It models performance with machine learning. It generates predictors with program analysis. And it uses even features that occur late in execution thanks to slicing. We showed that Mantis can do accurate and efficient prediction for smartphone applications. We hope that our work contributes to predicting system behavior better in broader environments. Thank you for your attention. I'm happy to take questions.
Actually, I have a question.
Sure.
So you showed a bunch of different applications, and one of them, chess, you had a harder time doing prediction.
Right.
And so chess was a pathological case for what you're doing, but is the kind of program chess is important? I mean, is this an indication of a class of applications that Mantis is going to have trouble with? Is this class of applications important, or?
I think there are a couple of reasons I can think of. So for example, in chess case, the program's nature is the computation time is kind of exponential. It's exploring all the game tree path. And what the Mantis basic modeling, machine learning model we are using is that most of reasonable programs we are looking at is polynomial or sub-polynomial. Because of that, we are using the Taylor expansion. So that part, we can have some troubles. And also, there are a lot of paths in Jest engine. Because of that, the slicing is harder to do compared to other programs.
But is this an example of, I mean, is there some class of applications that's like this that Mantis is going to have trouble with? Because I can see, running into the halting problem at some point.
Yeah, with static slicing, it's undisable. So there are a class of programs we cannot do well. For those cases, we have to, for example, have different models. For example, chess engine, after thinking about it, I think it may be better to have the model with exponential terms explainability. Yeah.
Thank you.
So.
Steve Cole from SUNY Buffalo. This is very interesting work.
Thank you.
And I have a question about your slicing. So on Android, it's event-driven. So I think the code is really fragmented. There are multiple entry points, and there's no single flow that you can predict.
Right.
Does it pose any challenge to your slicing?
For the evaluation we did, we are looking at a particular functionality of applications. For example, if user click a button, then it does some action. Okay. And how long does the action take? That's the kind of experiment we did. So looking at the entire program, involving Android framework like activity thread underneath, that would be more challenging. Okay. But we haven't done that, yeah. Okay.
So you basically look at inputs and then drive the experiments with your set of
That's right. We have a set of inputs, and then we drive that with our applications. Yes.
Okay. Thank you.
Thank you, speaker.